So people realized that you could kind of rearrange this for a more useful version of this equation. And the two people that came together and figured this out, their names were Henderson and Hasselbalch. If you take the negative log of both sides of this equation, well, minus log of hydronium is pH. Now, minus log of all of this stuff, you can break up into minus log acid over base, plus, if you will, minus log of Ka. This is what you can do with logarithms, and this is what people like doing. Well, minus log of Ka is pKa, and then you have minus log the acid over the base. And a lot of times people don't like using negatives, I think, in science and math. I don't know why. It's just an observation I made. It's hardly dogma. However, if you flip a logarithm numerator and denominator, you can change it to a positive. So pH equals pKa plus log base over acid is an equation we're going to use quite a bit. And again, if you flip base and acid, acid and base, you can change the sign. So that's what happened. This thing right here is called the Henderson-Hasselbalch Equation, and it's one of my favorite equations of all of chemistry. Woohoo! I know I need to get a life and get out and smell the air, whatever, but Henderson-Hasselbalch has a lot of really cool uses. The main use for Henderson-Hasselbalch is for buffers, all right, because you can use this expression to calculate the pH of a buffer. pH, the pH of a buffer, equals the pKa, and remember pKa is just minus log Ka, plus the log of the ratio of the base to the acid. It's an awesome expression because you can start, if you want to pick the buffer at a right pH, first of all, start by finding a pKa, which is close to the pH you want, and then you can fine-tune the ratio of base to the acid. If you need your solution to be a little bit more basic, you add a little extra base. If you need it to be a little bit more acidic, you add a little bit more acid relative to base. This is going to be an equation we're going to look at a lot in this chapter. I'll let you know, I'm known as the HH equation guy on the Mount Hood campus. I kind of babble about it a lot. You really don't have to use Henderson-Hasselbalch equation if you don't want to. There are other equations to get around it. However, I'm going to try my hardest to share why it is so useful and so important when you're dealing with buffers and then later even titrations. In the Henderson-Hasselbalch equation, the concentrations of the acid and bases aren't necessarily so important because it's a ratio. You can have in that ratio moles per liter over moles per liter, or you can have moles of base divided by moles of acid. It's the same container that you're holding the buffer, so the volume should be a constant, so you can get rid of the constant and think about it as moles over moles. Now this is really cool because all of the ice tables we've done, all the ice tables are based on moles per liter concentrations, but with the Henderson-Hasselbalch, you can actually just use moles over moles. So you have a choice. You can use molarity over molarity or moles over moles. Either way, it's up to you. If you dilute a buffer solution, i.e. add a lot of water, it doesn't affect the pH. And this is a wild thing that comes out of HH. If it's a ratio of moles over moles or molarity over molarity, in theory, you could turn your 30 milliliter buffer into a 3 liter buffer or a 300 liter buffer. And in theory, it shouldn't affect the pH because, again, it's the ratio of the base to the acid that's important, the moles, not the volume. So changing the volume with Henderson-Hasselbalch usually does not affect the expression. And that's kind of an interesting thing that I find still very counterintuitive. You'd think that changing the volume, you'd lower the concentrations, but it's a ratio, so it doesn't affect it. What it comes down to is that in the Henderson-Hasselbalch equation, you can use moles over moles or molarity over molarity to solve it. Either way is fine. And sometimes, as we'll see, especially in problem set 3, sometimes it's useful to have moles over moles, and sometimes it's useful to have molarity over molarity. You get to pick which one you want to use. Acetic acid has a Ka of 1.8 times 10 to the minus 5. It's pKa minus log of 1.8 times 10 to the minus 5, 4.74. We're going to prepare a buffer with acetic acid and sodium acetate. So again, notice we have a weak acid and its conjugate base. And we want the pH to be about 5. So what kind of ratio of base to acid should we have? All right, and there's 3 different choices, or 4 different choices down there. Now at first this might seem a little intimidating, but here's the thing. Remember, pH equals 2 parts. It equals pKa, and then the other part is this ratio, log of the ratio of base over acid. If the base over acid ratio was equal, you would have a log of 1. So for example, if base and acid concentrations were both 0.30, log 0.30 divided by 0.30 would be log of 1. Log of 1 is 0. So if the ratio were equal, pH would equal pKa. So if the ratio was equal, pKa would be 4.74, would also be the pH. pH would be 4.74. So we want a ratio, a pH of about 5. So a 1-to-1 ratio isn't going to work because 1-to-1, our pH would be 4.74, and we want to have a pH of about 5. We want our solution to become more basic. We want our pH of 4.74, if the ratio is 1-to-1, to become more like a pH of 5. So going from 4.74 to a pH of 5 is becoming more basic. There's still acidic pHs, but it's becoming more basic, and that's the important part here. So what that means is we need more base relative to acid, all right? More base relative to acid. That's what fine-tuning the log of base over acid is. More base over acid will make our pH more basic, all right? So when it says the ratio of base to acid, all right, well, we don't want more acid relative to base. That would make the pH go less than 4.74. It's going to be either B or D, all right? You want more base relative to acid. So the question is 1.8-to-1 or 5-to-1. My gut feeling says it would be B, not a big base change, because 4.74 to 5 isn't a huge change. So I would guess that answer is B. And sure enough, it is. Woohoo! If you don't believe me, and that's totally fine, notice here what I did mathematically. pH we wanted about 5, and pH of 5 equals pKa, which was 4.74, plus the log base over acid, all right? Well, 5 minus 4.74 is 0.26, and to get rid of that log, that log, you do the anti-log, the 10 to the x button, so 10 to the 0.26 equals base over acid ratio, and 10 to the 0.26, 1.8. So that means you need 1.8 times more base than acid. So if we had 1 mole of acetic acid, we would need 1.8 moles of the acetate ion. Or if you had 10 moles of acid, you would need 18 moles of base, something like that, that kind of a ratio. So in this problem, I kind of guesstimated that B was right. You can absolutely mathematically nail this down by doing this kind of process, and that can be really helpful. But remember, if you want a buffer which is more basic than the pKa, then you just want to add more base. If we wanted a buffer about a pH of 4, and that 4 would be more acidic than the 4.74 pKa, that means we would need more acid. Pretty cool. Here's a question. Let's figure out the pH when you add 1 milliliter of 1.00 moles per liter HCl, so 1 milliliter of a strong acid. We're adding it to a liter of pure water, and we're assuming the pH is exactly 7. We're also going to add that same 1 milliliter to a liter of buffer with an acetic acid concentration of 0.700 moles per liter and an acetate concentration of 0.600 moles per liter. This was the problem we did earlier, and we calculated it had a pH of 4.68, just as a reminder. Anyway, let's do the pure water first. Now remember, strong acids and water have incredible pH changes. We're only adding a milliliter, and that's not very much. So anytime you have a strong acid being added to pure water, all right, you need to find the concentration of the hydronium in the final solution. And what I would use here is an M1V1 equals M2V2. We start with 1.00 moles per liter HCl, and we're taking 1 milliliter of it out. We want to solve for the new concentration, M2, and the total volume is now going to be 1,001 milliliters. 1 liter is 1,000 milliliters plus the 1 milliliter we already had. That's where the 1,001 came from. Anyway, you solve for M2. That's the concentration of your hydronium, the H3O plus from HCl, 9.99 times 10 to the minus 4. pH minus log of that number, 3.00. So check this out. Your 1 milliliter of strong acid took the pH of the water from 7 down to 3. That's 4 pH unit change. That's a pretty significant value there for changing things. So again, strong acids will definitely affect the pure water quite a bit. Let's look, though, now at what happens when you add that same 1 milliliter of 1 molar HCl to the buffer, all right? And the buffer has acetic acid 0.700 moles per liter, and the acetate has 0.600 moles per liter, all right? And remember that the buffer was 4.68 to begin with. Now, if you're doing a problem like this, and you're going to do it the way I'm going to show you, you need to do what I call a double ice experiment, and I'll talk about what that means in a little bit. First of all, you have to do an ice table, which is based on stoichiometry, for adding the strong acid. Now remember, the hydronium, which is what HCl is, all HCl goes to hydronium, it's going to attack the base, the acetate, and in the process, it's going to make more of the weak acid, the acetic acid. Water is also created, but we don't really care about that. These reactions have really large Ks. They're very product favored, and you can justify using this stuff we talked about earlier, why K is so large, but trust me, it's very product favored, okay? So the first ice of the double ice is an ice table, all right? And you want to have hydronium, acetate, and acetic acid. In the first ice table, hydronium is a hunter-killer, and it's going to wipe out whatever is around it. So the moles per liter, which we calculated earlier, was that 9.99 times 10 to the minus 4 number. It's going to wipe itself out. It's going to all be used up. And in the process, it attacks the base, all right? So the base goes down as you add the strong acid to it. And so you have less base at the end. But as much as the base went down, the weak acid will go up. So you can see here that the acetic acid actually goes up to 0.701 while the base goes down to 0.599. There's no more strong acid left at this point, and now we have new concentrations of the base and the weak acid that goes along with it. So this is what I call the first ice of the double ice table. You just want to figure out the result of having a strong acid or a strong base attack a buffer. Strong acids attack the base, like here, and they make more weak acid. If you had a strong base, you would have the weak acid go down, and the weak conjugate base would increase a little bit. Anyway, this is the first ice. We're now going to need to calculate the pH of the new buffer system because we have new concentrations. So the second ice table is going to go back to the acetic acid Ka expression. The second ice table will look like the other ice tables we did earlier. You're going to have a minus X because the hydronium has to be made. Acetate will go up by X and stuff like that. So again, notice that in this double ice thing, which I'll talk about once in a while, the first ice is just dealing with the strong acid or the strong base. The second ice, which is what we're dealing with right now, is just a way to calculate hydronium from the new concentrations of the buffer substituents. Using those values at equilibrium, you can set them equal to Ka. Yes, 100 times Ka, which is 1.8 times 10 to the minus 5. I happen to have it memorized. I know I'm a dork, but anyway, 100 times K is certainly less than C, the 0.7 or 0.59 numbers. So you can ignore those little minus X. This also says, hey, before we had the HCl, the hydronium was only 2.1 times 10 to the minus 5. That's from the problem we did earlier. So again, adding that number to 0.701 or 0.599 or subtracting it, it makes no difference. Again, by sig figs, you have to cut them off a lot faster than that. So ignore the plus x, ignore the minus x. You end up with H3O plus, the hydronium, equals acid over base times Ka, the acid 0.701, the base 0.599, and the Ka for acetic acid, like I said, 1.8 times 10 to the minus 5. So when you plug this in, the hydronium concentration comes out to be 2.1 times 10 to the minus 5. And pH minus log of that number, 4.68. But guess what? That's the number we had earlier when we didn't have any HCl. So what this means is that adding HCl to this buffer didn't change the pH at all. It did make the acetic acid concentration go up a little bit and the base concentration go down a little bit. But the overall change in the acid to base was still pretty constant relative to it was. No change in pH. So buffers are really good at resisting changes to pH. And remember, this 1 milliliter of HCl made the pH go down about 4 units to pure water. So this isn't like a small amount of acid per se, but with this buffer, nothing happened. Buffers are cool. I recommend when you add strong acids or strong bases to buffers that you use another version of the Henderson-Hasselbalch equation. So I want to show you an alternative way to get around double ice problems like we just went through. In the handout for Henderson-Hasselbalch and buffers, there's an expression which looks like this, where it says pH equals pKa plus log. Now remember that the base over acid in the HH equation can be moles or moles per liter. In this version, you must use moles, but if you use moles of base over moles of acid, well, the moles of strong acid will attack the base, but as much as they lower the base, they will also raise the weak acid. So you can see here what's happening. The strong acid is lowering the base and it's increasing the weak acid, which is kind of cool. Anyway, pH equals, or pKa, minus log of Ka, 4.74. Well, if you figure out all of these numbers then, pH equals pKa, 4.74, plus log, concentration, 0.600, because we have 1 liter here, so it's exactly that. Anyway, 4.67 is the pH you get. Now, double ice gave 4.68. So some scientists say, oh, well, double ice is better and Henderson-Hasselbalch is lame and stuff like that. I don't agree. That last number is the doubtful digit. It's the one that's uncertain. There's always a plus or minus at that last spot. And going from 4.67 to 4.68 is certainly not a big deal. It's not going to make an experimental difference because that's always an uncertain value. Henderson-Hasselbalch, it was going to save you time and give you really good results. So just realize that sometimes you will get different results from HH relative to double ice, but man, you'll be spending your time looking at other things instead of doing double ice. Anyway, this expression is also in the Buffers and Henderson-Hasselbalch guide, and I do recommend you check it out. This expression is the one you want to use when you add a strong acid to a buffer. The strong acid lowers the concentration of the base, but it increases the concentration of the acid. I'm using concentration, but in the actual HH equation here, you must use moles, okay? So make sure you use moles if you're using strong acids or strong bases. There is an equivalent expression for adding a strong base. The strong base lowers the weak acid, and in the process, the conjugate base, the weak base, is increased. So both of these equations are really cool. When I think about the HH equation, the Henderson-Hasselbalch equation, I think of 3 equations actually. pH equals pKa plus log base over acid. That's for the normal buffer equations, which is what most people use. On the other hand, if you want to find the pH upon adding a strong acid, you would use this equation right here. If you add a strong base to a buffer, you'd want to use this one right here. Those 3 equations allow me to do so much in chemistry when it comes to this kind of stuff, and I do recommend it. Just make sure you use moles in these 2 versions. Don't want to use moles per liter. Here's a question. Adding a small amount of strong base to a buffer results in. Okay, let's stop right there. You're adding a base, a strong base, okay? So anytime you add a base, your pH should go up, all right? So in the answers down there, which I haven't even looked at, I'm going to automatically eliminate C, D, and E, because if you add a base, the pH is going to go up. It's not going to go down. So C, D, and E, whatever they are just silly, okay? So it's going to be A or B. pH is going to go up. So let's look a little more carefully now at A and B. So it's going to go, you're going to have an increased pH due to the strong base, B, an increased pH due to the weak base of the buffer. Okay, I would definitely argue that answer B is the correct answer. The strong base attacks the weak acid in the buffer. So the amount of weak acid goes down, and in the process, you end up making more of the weak base. So any pH change you see will be the result of the weak base and acid that's still left ratio. It won't be the effect of the strong base, all right? Strong base makes it happen, but it's not the reason why the pH gets bigger. So this is kind of a cool thing and stuff to think about. Again, you add a base, you're going to have a bigger pH, but it's not from the strong base. In this context, it's from the weak base that's present. You have more of it, going to have a bigger pH. Here's actually pictures of Henderson-Hasselbalch. Took me a while to find them. They look like kind of cool old dudes. But anyway, I digress. Here's a question you might have. You want to create a buffer with a pH of 4.30, all right? And if you want to figure out hydronium would equal 10 to the minus 4.30, 10 to the minus pH. That's 5.0 times 10 to the minus 5. So you go to the lab and you're like, what kind of system should we use? Well, you must use a buffer system, a weak acid and its conjugate. We want to pick one where hydronium is about equal to Ka or pH is about equal to pKa. We saw how pH in Henderson-Hasselbalch equals pKa plus log base over acid. So if you start with a pKa close to your pH, that'll be good. And then you can fine-tune that base to acid ratio later. You can also think about it as the hydronium about equal to the Ka, and either way is fine. So here's the possible buffer systems you have in your lab. And I'll be honest, every time you go to the lab, it's kind of like going to the fridge. You may not have everything you want. So in our chemical system, chemical stockroom right now, we have hydrogen sulfate and sulfate. That would be a buffer system. We have the acetic acid acetate solution, and we also have hydrocyanic acid and cyanide as possible buffers. Well, here's their Kas and here's their pKas. And if we want a pH about 4.3, then we want to find a pKa as close to that pH as possible. So you can see that 4.74 is certainly close to 4.30. That would be a good pick. Now you can also compare Ka to the hydronium, and you can see that the Ka for acetic acid, 1.8 times 10 to the minus 5, that's pretty close to 5.0 times 10 to the minus 5. If you use the hydrogen sulfate buffer, your pH would come out to be more acidic. The initial pH would be about 1.92, and that's too acidic for what we want. On the other hand, if you use the hydrocyanic acid's cyanide solution, all right, that would give a pH initially which was too basic. The pH would come out to be about 9.4. So we want the one in the middle, all right? You want the acetic acid acetate system to use. That pH is that pK, is closest to pH, or the hydronium's closest to Ka. So try to pick a buffer which is close to your desired pH, and then you can fine-tune it from there. Now, in our case, if we started with acetic acid acetate, the initial pH would be about 4.74 if the ratio of base to acid was 1:1. We want 4.30. We want it more acidic, so we would want to add more of the weak acid, acetic acid, relative to acetate. That would make our 4.74 number get closer to 4.3. Let's go back to that thing. We want to create a buffer system, again at pH of 4.30 or hydronium 5.0 times 10 to the minus 5 using acetic acid and acetate. Equal moles of acetic acid and base would again create a pH of 4.74. That's what the pKa is for. So if we want to find the ratio of acid to base needed to get the ratio to the buffer pH to 4.30, we can absolutely use the Henderson-Hasselbalch again. So Ka equals hydronium times acetate divided by acetic acid. If you rearrange that, hydronium is going to be 5.0 times 10 to the minus 5 equals acetic acid divided by acetate times 1.8 times 10 to the minus 5. So what we're trying to do here is we want to solve for the ratio of the acetic acid to the acetate. So if you take 5.0 times 10 to the minus 5, divide it by 1.8 times 10 to the minus 5, you're going to get a ratio 2.8 to 1. And 2.8 to 1 is the amount of acid you need relative to the amount of base to make the pH go to 4.30. So if you have 2.8 moles of acetic acid for every 1 mole of acetate, you're going to end up with a pH which is close to 4.30. You could have also done this with the Henderson-Hasselbalch equation, pH equals pKa plus log base or acid. You would have solved for the base over acid ratio, and you should come up with 2.8 that way as well. On the last slide, we saw that the ratio had to be 2.8 moles of acid for every 1 mole of base. So if we had, say, 0.10 moles of sodium acetate, we would need 2.8 times that number, or 0.28 moles of acetic acid, and that would give us our desired 4.30 pH. This is the way you do it with the Henderson-Hasselbalch, and again, either way you want to do it is totally fine. But you can see in this example, pH desired 4.3, pKa 4.74. We solved for log of conjugate base over acid. That came out to be a ratio of 2.8, and again, either way is totally fine. In Henderson-Hasselbalch, it's initially base over acid, so if you flip it, you can put it on the other side to make it acid and base. Here's another kind of problem you might run into. Let's say you had 8.4 grams of sodium hydrogen carbonate mixed with 16.0 grams of sodium carbonate. Now, if you pull off the sodium ions, all right, you can see that hydrogen carbonate has more hydrogens than carbonate does. So hydrogen carbonate here is the acid, and the carbonate there is the base. And again, we ignored the sodium. Sodiums are just spectator ions. And the question here, what is the pH of this solution? And there's several different ways to solve it.
To prepare our buffer solution, we first weigh our conjugate pair, 16.0 grams of sodium carbonate, the weak base, and 8.4 grams of sodium bicarbonate, the weak acid. We dissolve these solids in 100 milliliters of water. The final buffer solution has a volume of about 120 milliliters and a pH of 10.5.
This is a good problem to try on your own, all right? And what I would do in this problem is I would use Henderson-Hasselbalch, pH equals pKa plus log base over acid. You'd have to look up the Ka for hydrogen carbonate from the table and turn that into a pKa. You'd also have to turn both of those gram amounts up there into moles. And when you turn grams into moles, by the way, you should put the sodiums back in, all right? Don't cross them out like I did. Yes, so make sure you use sodium hydrogen carbonate and sodium carbonate. Don't exclude the sodiums. But anyway, you'll get the ratio moles of base over acid. pH equals pK plus log base over acid. You should get 10.50. Try it out. If you don't get it, email me your work and I'll see if I can help you to figure out how to get this answer.